You ever watch a crowded highway from an overpass during, like, peak rush hour?
Oh, yeah. Just a complete sea of red taillights, burning fuel, and going absolutely nowhere.
Right, exactly. You're looking at all this latent kinetic energy, right? I mean, thousands of cars engineered to go 80 or 90 miles an hour, completely paralyzed.
Yeah, and it has nothing to do with the actual power of the engine.
Yeah, not at all. They
Yeah.
are sitting there because the physical space of the road itself is the limit.
The infrastructure just physically cannot handle the sheer volume of traffic trying to pass through, a specific point at a specific time.
And right now, inside the microscopic architecture of the world's AI data centers,
Yeah.
we are hitting the exact same thing, the ultimate digital traffic jam.
It really is.
So the blueprint you brought us today, it's this densely packed dispatch from a Digitimes report, and it reveals that the tech industry is actively trying to replace these crowded digital highways with basically light-speed bullet trains.
Yeah, but they have hit a really severe microscopic roadblock. The text you brought us centers entirely on a structural bottleneck in something called co-packaged optics, or CPO.
Right. And since today is April 5th, 2026, I mean, this is not a theoretical problem for the next decade.
Yeah.
The source you shared with us predicts a massive industry-wide tectonic shift happening this exact year.
This year. Yeah.
So the mission for this deep dive is to, really dive into the physics of this transition, look at the structural roadblock the industry is actively colliding with, and prepare you for a technological tipping point that is basically unfolding around us right now.
And it is so rare to get a real-time look at a global supply chain bottleneck while the industry is actively fighting to solve it.
Right, usually we just don't hear about it.
Exactly. Usually the consumer only hears about these transitions after the new hardware is already, sitting in our devices.
Yeah, so true. So to understand the severity of this bottleneck, we first really have to look at the sheer scale of the shift. The Digitimes report provides a staggering forecast.
It really is staggering.
By the end of 2026, over 50% of data center transceiver sales will come from silicon photonics or SiPh modules.
Half the global market. I mean, think about
Yeah.
the millions of servers operating in data centers worldwide.
It's massive.
A sudden pivot of that magnitude to a single specific hardware technology is highly, highly unusual. Hardware cycles normally take a decade to flip,
Right.
but this is happening practically overnight.
Okay, let's unpack this. Historically, transceivers have always relied on copper.
Yeah, exactly.
We push electrons down a wire. You have your computing chips, the massive GPUs running these complex AI models, generating just oceans of data.
Right. Huge amounts of data.
And the transceivers basically act as the critical train stations at the edge of the chip, loading those electrical signals onto cables to send across the network to other chips.
And, I mean, copper has been the foundation of computing for decades. It is cheap, it's reliable, and we know exactly how to manufacture it.
We've mastered it.
We have. But as AI models scale, copper hits immutable laws of physics. When you attempt to push the massive parallel bandwidth required by modern large language models through copper wire, it generates immense heat.
Right, they run super hot.
Yeah, and more importantly, you suffer severe signal degradation over distance,
So you are effectively melting the tracks trying to run too many heavy trains.
which forces the shift to silicon photonics. Instead of pushing electrons over copper, SiPh takes those electrical signals, translates them into pulses of light using microscopic lasers, and shoots them through fiber optic cables.
Swapping standard trains for light-speed bullet trains.
What's fascinating here is the timeline. The 50% market dominance forecast for this year means this transition to light is not just some experiment, it is a desperate necessity.
Wow, a desperate necessity.
Yeah, because AI models require thousands of chips to talk to each other simultaneously to train and operate. If those chips cannot communicate instantaneously, the entire cluster basically just sits idle waiting for data.
Just burning money.
Exactly. Copper is the traffic jam. Light is the open highway.
And the data centers are buying these silicon photonics modules basically as fast as the foundries can manufacture them. But the Digitimes headline puts a huge emphasis on bottlenecks in CPO and silicon photonics, specifically isolating testing and optical alignment.
Yeah, because if dropping a microscopic laser slightly off-center during manufacturing means throwing away a multi-thousand-dollar piece of silicon, the bottleneck isn't just a physical hurdle anymore.
It becomes a massive financial wall.
Exactly.
Here's where it gets really interesting, though. Wait, I need to play devil's advocate for a second here.
Sure, go for it.
We have known how to transmit light through fiber optics for decades, right? I mean, the entire internet backbone under the ocean runs on fiber optics.
Very true.
So why is simply testing and aligning a laser on a chip suddenly causing a global supply chain bottleneck? We aren't reinventing the laser here.
No, we aren't.
It feels like we built a factory capable of churning out 1 million supercomputers a day, but the entire assembly line is paused at the door because, like, manually plugging in a fiber optic cable is taking too long.
Well, if we connect this to the bigger picture, your factory analogy actually captures the literal truth of the manufacturing floor. You brought up CPO earlier, co-packaged optics.
Right.
That concept of packaging is the double-edged sword that's causing the bottleneck. Historically, the transceiver, the train station in your analogy, was a separate box that sat a few inches away from the main computer chip on the motherboard.
Okay, a few inches away.
But driving an electrical signal across those few inches of motherboard to reach the laser still uses way too much power and creates too much heat.
Ah, so the distance itself is the enemy.
Exactly. So engineers realized they needed to move the train station directly next to the city. Co-packaged optics literally means bonding the optical laser module directly onto the exact same piece of silicon substrate as the GPU itself.
Oh, wow. So they're basically sharing the exact same real estate.
Right, it eliminates the distance problem entirely.
But I'm guessing it creates a monumental physical problem. Optical alignment.
You nail it. When you deal with silicon photonics at a co-packaged scale, you are attempting to perfectly align a microscopic glass fiber with a microscopic laser channel on a piece of silicon.
How microscopic are we talking?
We're talking about precision at the submicron level. For context, a single red blood cell is about 7 microns wide.
Wait, really? So we were talking about tolerances smaller than a single biological cell?
Yes, if that alignment is off by even a fraction of a micron, the laser light just scatters into the silicon substrate. The signal degrades instantly and the data is completely lost.
Wow, so this is definitely not like plugging a standard USB cable into a laptop where it just snaps into a port.
Not even close. It requires incredibly complex robotic machinery operating in pristine clean rooms just to hold these components steady while they're bonded.
I can't even imagine.
And the bonding process itself can cause microscopic shifts, As adhesives cure or metals cool down, things move.
And then comes the testing phase that was highlighted in the source.
Right. To test a traditional electrical connection on a microchip, you basically just apply a voltage and measure the resistance. You use automated machines with tiny electrical probes that physically touch the chip.
And that's super fast, right?
It is incredibly fast.
But you cannot just run an electrical current through a laser channel to see if the glass is aligned properly.
Exactly. You have to literally inject a physical laser into the module. You have to measure its exact wavelength. You have to ensure no stray photons are reflecting backward into the laser cavity, which, by the way, can destroy the light source.
Oh, wow. It can just blow it out.
Yeah, it breaks the hardware. And crucially, you have to measure the thermal output.
Because lasers generate a lot of heat. And you just placed that heat source on the exact same piece of silicon as your delicate computing logic.
Bingo. If the thermal dissipation isn't perfect, the heat from the laser can literally warp the silicon at a microscopic level.
Which would move the alignment.
Exactly. It instantly throws that submicron optical alignment out of whack and destroys the chip. Testing a co-packaged optic module requires assessing multiple physical domains all at once.
Like what?
Electrical pathways, photonics, and thermal dynamics, all at the same time.
This is the ultimate irony of the AI boom. We are talking about building digital superintelligences capable of processing, like the sum of human knowledge.
Yeah.
Yet the entire timeline relies on whether a robotic arm can successfully glue a microscopic glass hair to a piece of silicon without missing by half a micron.
It's crazy when you put it like that.
Software's greatest leap is entirely at the mercy of physical plumbing.
That is the reality of the hardware supply chain. The theoretical ideas almost always outpace the physical manufacturing capabilities.
Right.
Whoever solves this testing and alignment bottleneck basically controls the main valve for all future AI infrastructure.
Which brings us directly to the players actively trying to solve it. I mean, the companies that can build the microscopic tweezers and testing probes to fix this aren't just selling factory tools. They are basically holding the keys to the AI revolution.
Absolutely.
The source actually lists the specific entities sitting right at this critical choke point. We've got form, keys, ACE, EYY, and AEHR.
Yeah, these are the organizations tasked with turning a meticulous laboratory-grade optical alignment procedure into a high-volume, automated manufacturing process.
And the text specifically calls out AEHR for its exposure to SiPh yields and testing bottlenecks. And it notes that right now, in 2026, we are still in, and I quote, quite a few qualification cycles.
Right.
So what does this all mean? How do these specific companies actually factor into solving a submicron alignment problem?
Well, this raises an important question about how high-tech semiconductor manufacturing actually scales up to meet global demand. Let's tackle yields first.
Okay, yeah. What exactly is a yield in this context?
So when foundries manufacture these chips, they don't just build them one at a time, they print hundreds of them simultaneously on a single giant silicon wafer.
Right, like a huge shoot of them.
Exactly. But because the optical alignment tolerances are so unimaginably tight, the failure rate on that wafer is going to be exceptionally high.
I can imagine. Just one tiny mistake.
Yeah, a microscopic vibration on the factory floor or a slight temperature fluctuation during the bonding process means the module is just dead on arrival.
Wow.
So the yield is simply the percentage of modules on that wafer that actually survive the manufacturing process, pass the stringent optical tests, and function properly.
And currently, those yields are the major hurdle holding back the 50% market shift.
Precisely. If you are throwing away 60 or 70% of everything you manufacture because the light leaks into the silicon, your product is going to be astronomically expensive.
Yeah, the math just doesn't work.
You simply cannot produce enough volume to satisfy a market demanding millions of these transceivers.
This is where the specific companies mentioned in the report come into play, right? And they aren't all doing the exact same thing.
No, they occupy different, very vital niches in solving the bottleneck.
Okay, breaking down for us.
Sure. Take Keysight stock, ticker CURYS, and Form Factor, ticker FORM. These companies specialize in the highly advanced testing equipment and the microscopic probe cards that actually interface with the silicon.
Oh, so they are building the tools to test the invisible.
Basically, yeah. They engineer the machines capable of injecting the light, measuring the thermal output, and confirming whether that submicron alignment was successful. And they have to do all of that without physically damaging the delicate chip in the process.
Which sounds impossible.
It's incredibly difficult.
Yeah.
They have to automate a testing process that used to be done manually by optical engineers in labs.
And what about the physical packaging itself? Like getting the laser and the silicon permanently glued together at scale.
That falls heavily on companies like AEHR and ATEY. They are massive players in outsourced semiconductor assembly and test. They're basically the mechanical engineers of the micro world.
Okay, I see.
They handle the complex logistics of co-packaged optics, taking the raw silicon wafers, the microscopic lasers, the fiber arrays, and developing the automated robotic processes to assemble them reliably in really high volume.
Which leaves AEHR, the company specifically tied to SiPh yields in the text. What do they do?
AEHR focuses on a critical phase called burn-in testing.
Burn-in testing.
Yeah. Before a tech giant deploys a massively expensive AI server rack into a data center, they need absolute certainty it is not going to fail under continuous load. So AEHR figures out how to stress test these photonics at scale.
Wow, it sounds like a torture chamber for microchips.
It essentially is. They build these specialized testing chambers where they load thousands of these optical modules at once, and they run them hot.
Like actually physically hot.
Very hot, pushing maximum power and thermal load through them continuously for hours or even days. The goal is to deliberately trigger early failures.
Weeding out the weak links before they ever leave the factory floor.
Exactly, because by identifying which modules fail under stress and exactly why their optical alignment shifts under thermal load, that data loops right back into the manufacturing process.
Oh, that makes total sense.
Yeah, it helps the foundries tweak their assembly methods, which directly improves the overall yields we talked about.
So it is a complete ecosystem trying to unblock the drain. You've got the probe makers, the packagers, and the stress testers. But the source notes we're currently sitting in quite a few qualification cycles. That kind of sounds like the industry is stuck in a waiting room.
It is a waiting room, yeah. A qualification cycle is an intense, prolonged audition process. The massive tech giants building these AI data centers simply cannot afford hardware failures.
Right, the stakes are too high.
Way too high. If a co-packaged optic transceiver goes down in the middle of routing data for a massive AI training run, the entire computational cycle might be corrupted. That costs millions of dollars in wasted energy and compute time.
Wow. So they aren't just going to buy a million units of a new highly sensitive optical technology on day one just because the supplier says, hey, it works.
Not a chance. They require the manufacturers to send them massive sample batches. The data centers then install these modules and put them through grueling real-world stress tests.
So they are verifying the work of form and AEHR.
Exactly. They evaluate if the testing and alignment processes developed by FormFactor, Keysight, ASE, and the burn-in tests from AEHR are actually producing reliable components that survive the harsh real environment of a functioning data center.
It's the final, agonizing holding pattern before mass adoption.
Yeah.
The technology is out of the lab, it is off the initial assembly line, and the end buyers are basically actively trying to break it to see if it holds up.
And this brings us to the explosive final sentence of the source material you provided.
Yes, let's get to that.
It is a perfect storm of immense demand meeting a very stubborn physical bottleneck. But despite the fact that the industry is currently sitting in these rigorous qualification cycles, the report explicitly states, and this is a big deal, expect mass order ramp to hit any time.
Anytime. I mean, that implies the audition is basically over, right?
It is a massive signal to the market. It means the qualification cycles are succeeding. The end buyers are finally seeing the high yields they require.
Wow.
The testing bottlenecks and the optical alignment issues are being systematically dismantled by the equipment players we just discussed.
So the data centers are ready to pull the trigger.
Exactly. Moving from testing hundreds of sample units to demanding millions of commercial units. A mass order ramp means the supply chain has finally figured out how to manufacture, align, and test light-speed infrastructure at a global scale. The dam is basically about to break.
It is the moment the digital traffic jam finally clears and all that trapped kinetic energy is released simultaneously. We're looking at a massive tipping point here, not just for the semiconductor companies involved, but for the entire underlying infrastructure of artificial intelligence.
The physical limitations that have been throttling data transfer speeds, the heat of the copper, the latency of the electrical signals are on the verge of being completely bypassed.
Incredible. So let's summarize the journey of this deep dive. You brought us a tightly packed blueprint showing a massive shift happening right now in 2026.
Yep.
Over 50% of data center transceivers are moving to silicon photonics. The industry is desperately upgrading to light-speed bullet trains to handle the immense data demands of AI clusters. But, as we discovered, the physical reality of co-packaged optics, the microscopic submicron tolerances required to glue a laser to a chip without it melting or misaligning, created a massive testing bottleneck.
Right, the low yields were the challenge. But the ecosystem of testing, packaging, and burn-in companies are actively proving to the data centers that they have solved this physical plumbing issue.
And with the mass order ramp expected at any moment, the shift to light is totally imminent. Thank you for sharing such a timely, high-stakes piece of information with us.
Absolutely.
It is incredibly fascinating to look at a microscopic alignment problem, literally a tolerance smaller than a human cell, and realize it is the single linchpin holding back the macroeconomy of artificial intelligence. We have talked extensively about the hardware today. The lasers, the testing probes, the thermal warping of the silicon.
All the plumbing.
Exactly, the plumbing. But I want to leave you with a final thought to mull over as you go about your day. Think back to that incredibly frustrating highway traffic jam we talked about at the very beginning.
Sitting in traffic, going nowhere.
Right. If the testing bottlenecks for co-packaged optics are fully solved tomorrow and that mass order ramp hits, clearing the lanes and instantly multiplying the bandwidth at which AI models can communicate with each other, well, how will this sudden massive acceleration in data transfer speeds permanently alter the physical limits of what AI models can actually achieve next?